Good morning, everybody, and welcome to the second part of our introduction to central systems for heat pump water heating. This is sort of the how to do heat pump water heating for multifamily and commercial. I'm Katie at the Lighting Design Lab. Any questions that you have, feel free to put in the chat or reach out to us later at lightingdesignlab@seattle.gov. And with that, I will send it over to Sean to moderate. It's just an hour, so we got to get started.
Hi everyone, my name is Sean Hoffman. I'll be moderating today's session. I'm from DNR International as a project associate, and I'll be taking in all the questions that you have. So send them in through the question channel or through the chat, and I will bring them up to Colin at an appropriate time. We don't have that much time today, so be sure to get them in early so we can find an appropriate time to get to them. Also, if you have any issues with links or audio, reach out to me in the chat and I will help you out as best as I can. Without further ado, Colin.
Thank you, Sean. Welcome everyone to another session on commercial heat pump water heating systems. My name is Colin Grist. I am a mechanical engineer who works at Ikea, a mechanical energy and plumbing research and design firm that really specializes in high efficiency building systems, one of which includes commercial heat pump water heating systems. So I've been working with Ikea for the past 8 years, very involved with the water heating world. And so I'm here today to talk to you about how to implement these commercial heat pump water heating systems in the buildings you're working on, because we learned in the last week's seminar that these are now being required by code in some jurisdictions. And we also learned that there's an immense amount of energy savings that we can capture with one of these much more efficient systems. So today we are going to continue that discussion and talk about how to implement these systems successfully in your building and some key considerations. So our objectives for today, we're going to cover building types and applications. We are really focused on multifamily buildings for this session as it's geared towards Seattle City Light, and heat pump water heating systems are now required for R1 and R2 occupancies, and that means hotel, motel, and multifamily. We're also going to cover the 4 system components that make up a commercial heat pump water heating system and talk a little bit about the key design considerations for those components, as well as how to design and size a system correctly, as that's another key design consideration we have when working with this type of equipment. And then the last thing we're going to touch on is some Seattle Energy Code updates and where you can find more information about the requirements in your jurisdiction, if that's Seattle or other incentive updates that the code is offering or the utilities are offering. So the first thing we're going to dive into is building types and applications. And we are once again focused on multifamily buildings. And at Ikea, we've successfully implemented multiple commercial heat pump water heating systems across a wide range of multifamily building types. Low rise, mid rise, and high rise are all very applicable to this technology. You might approach the problem a little bit different, size the heat pumps a little bit different depending on the type of building, the size, the height of that building, and other requirements that come with that additional height and pressure zone. But all in all, commercial heat pump water heating systems are really great, highly efficient systems that will dramatically reduce the energy use of domestic water in multiple types of multifamily building. But we do have other building candidates that are really well positioned and suited for commercial heat pump water heating systems, and will also result in significant energy savings. Oh, I apologize. We have a graphic that's not working, but imagine there's a graph on the screen today, and looking at building types that use a lot of hot water, we typically have hospital, residential, healthcare, fire stations falling into those categories. These are buildings that typically have a 24/7 occupancy, and the people occupying those buildings use water in their day-to-day procedures. Whether that's in a hospital for cleaning, sanitation, or other hospital services, residential, primarily using hot water for cleaning up, taking showers, and doing our laundry and so forth. Healthcare, we still have a lot of hot water usage as we're trying to keep people healthy or make them healthy again. And so there's hot water usage there around cleaning and sanitation and other procedural aspects. And then fire stations, those folks are basically in those fire stations 24/7, swapping out on different shifts, but they are often using hot water to clean the facilities, clean up after cooking, or taking showers after they are in the field working on an emergency activity. So there's a lot of high water usage in this left-hand column here, and so heat pumps will result in really significant energy savings in this type of building type and application. The building types on the right-hand side of the screen, libraries, schools, offices, and police stations, are also really great applications for domestic heat pump water heating equipment. But we typically have a little bit less water usage in this type of building because they're either not 24/7 or they're not occupied every day of the year 24/7, or in an office, right? We're not often taking showers like we are in our residences. So typically a little bit less water usage, which means over the course of the year, the savings is a little bit less for a heat pump, but you're still going to save a lot of energy and money overall, regardless of the building type that commercial heat pump water heating system is serving. So a lot of great building types and applications or heat pump water heaters are ideal for numerous building types and different occupancy types. And so the next aspect of commercial systems that we're going to dive into is understanding the 4 components. And this is an attempt to get us all understanding about those 4 components and what they're really serving in the building or in that domestic use for hot water. And so the primary or the number 1 component that we always start with is the primary heat pump water heater, right? This is the focus typically of the system, the main piece, the engine in the car. The primary heat pump water heater is actively moving heat into water, and typically it's storing it in a primary hot water storage tank. And so after we've moved heat from air with an air source heat pump, we're going to dump that heat into water for a domestic application. And so that primary heat pump is coupled with that primary hot water storage. And one quick note about heat pumps is they're not instantaneous water heaters like you can get with an electric or a gas instantaneous heater. And so we'll always need some type of storage volume to store that hot water after we extracted it from the air at a super high efficiency. The third component, which is often new to some of us, but we've dealt with it in the past if we've worked on plumbing systems, is the temperature maintenance system. And what I mean by a temperature maintenance system is in these larger commercial buildings, we either have to circulate the hot water through the distribution piping at a slow flow rate so that the people towards the end of that distribution line have hot water within a meaningful response time. So we're typically targeting 10 to 20 seconds of response time. So as soon as someone opens that hot water tap, there's going to be hot water coming out of that fixture, hopefully within 10 seconds after opening that tap or turning on your shower. And so to do that, we typically have a hot water circulation pump or some other means to maintain temperature in that hot water distribution network of piping. In our engineering deep dives, we cover a lot of the fine details that are important and associated with this temperature maintenance system. As we've seen, it's a critical aspect of a reliable and efficient heat pump water heating system. But right now, I just want to bring your attention to that type of system and that it exists in both our heat pump water heating systems as well as our electric resistance or gas water heating systems. That temperature maintenance equipment and system was typically just integrated with that primary equipment that we're noting here as the primary heat pump water heater. And then the last of the four components that we're going to discuss today is the control system. We need some way to turn on and off the heat pumps based on a load in the building. And typically we do that with controls. There's two primary types of controls that we'll cover today, but we can either have a control system that's integrated with that heat pump water heater, typically the primary heat pump water heater, or we can have a standalone third-party control system with communication lines going to all the devices in our system. So with our four components, we are starting with the primary heat pump water heater. And the first thing to really understand is that heat pump water heaters in general come in two different product types. One is the unitary type of device, and we might be familiar with this in a residential application. But this is a heat pump water heater that is located on top of a storage tank. So our heat pump water heater is up top there, and our storage tank's down low here. I have one of these in my basement of my Seattle home, and it is a really great device that has dramatically reduced my and my wife's energy usage with regard to domestic hot water. So these are great pieces of equipment. They're all packaged together. The compressor, tanks, controls is all provided in a single package, either from a big box retailer or your local plumbing supply house. But there are also split system heat pumps, which we have on the right side of the screen here. And by split system, all we're doing is we're splitting out the heat pump, which has the compressor, evaporator, and other components in it from that storage tank. And so right here, I'm showing a Sandin or Sandco 2 heat pump water heater, which is again a residential sized heat pump water heater. And the main difference here is that it's split apart, and this heat pump can be located remotely to the storage tank, which gives us a lot of great design flexibility. So we might be looking at this type of system for most applications. And that brings up another point, is sizing of these pieces of equipment. Typically, the unitary products are more applicable, more sized for a residential single-family home application. And the split systems, they do come in residentially sized single-family home applications or sized for that, but they also are the primary type in the larger commercial product range. So have you seen a Colmac or a Mitsubishi, a Nile, or a Rheem A.O. Smith heat pump water heater? They're typically larger split systems for those commercial applications. And so we'll show some of those today and cover a few points about them. But all in all, we have two types of heat pump products. Unitary, it's all packaged together. Split system, the heat pump is separated from that storage tank. So looking at this unitary product, we have a residential integrated or unitary heat pump water heater shown on the screen. We can see that there's a heat pump on top and we have some components with that heat pump to move the heat from air into water. And so we typically have a fan on an evaporator, a compressor, and a handful of other components to do that. Then we have this hot refrigerant, and we need to transfer that heat from the hot refrigerant into water. So there might be another heat exchanger, a condenser wrapped around this tank. And so that's how that heat pump's working, is it's taking heat out of the air, putting that heat into this refrigerant, which then is super hot, and transferring that heat from the refrigerant to the domestic water that's in this tank. And we might also have a backup element, electric resistance element for some of these products to deal with low ambient air conditions, to provide redundancy in that system design. Now let's look at this residential product and compare it to our larger built-up commercial systems. So we have a picture of Jackson Apartments on the left-hand side of the screen now. And this is the Jackson Apartments is close to 500 residential units in a multifamily building, 7 stories tall, but it's split into an east and a west wing. And so right now we're looking at the east wing system at Jackson Apartments. And we have very similar or the same components that we do as a residential heat pump water heating system. So like I noted, our heat pump is on top of the storage tank in this small unitary integrated heat pump water heater product. And in our larger commercial system, we might have one heat pump or multiple, like I'm showing here, as these larger gray silver boxes. And so these heat pumps still have water connections that are going to a system of storage tanks. And they also have a ducting connection on top there for as this is an air source heat pump. So that is part of the exhaust duct network. So like we have a heat pump in our residential product, we also have it, of course, in our commercial built-up system. Same thing is true with the storage tanks. I said earlier that heat pumps are not instantaneous water heaters. It's a process. It takes time to move that heat into water. And so we typically will have a storage tank or multiple storage tanks, just as we do in that residential product. So here in the Jackson Apartment case, we have 3 white storage tanks back here on kind of the back right of that photo. I mentioned that integrated products often come with a backup electric resistance element. This system at Jackson Apartments, we wanted to design redundancy into it, so we also provided a backup system here. This is an electric resistance water heating tank that's in line after these storage tanks, so that if the temperature drops over a period of time and the heat pumps aren't functioning for some reason, or they're out on a service call, we have a way to ensure hot water is delivered to the apartments by engaging that electric resistance backup element in that tank. And then the last of the 4 components, we have a control system. Typically it's mounted directly on the residential integrated heat pump. You might have a few temperature settings that you input there, and whether it's an eco, high efficiency, or another mode of operation. In a commercial system, we might have a more built-up control system, or we might use the controls that are within the heat pump. And so although it's one of our components, there's a few options there for making this system function reliably and efficiently in multiple buildings. But that control system is communicating typically with the storage tanks to turn on and turn off based on the domestic water load in the building. So all in all, the commercial systems, although they're much bigger, louder systems typically, and they can serve more occupants or tenants in a building, they're very similar to our residential products that we might be a little bit used to in our single family home applications. And so We are diving into the components here, and we're going to talk a little bit more in depth about the primary heat pump water heater first, and then move on to the primary storage, temperature maintenance system, and back to the controls. So our primary heat pump water heaters are moving heat from a source of air typically into water. That's what we call an air source heat pump water heater. We can also have a water source heat pump water heater where we're moving heat from water as a source into water as our for a domestic application. But all in all, heat pumps are much more efficient than gas or electric resistance water heaters, as they are moving heat, not making or generating heat. It's much more efficient to move heat than it is to generate heat. And air source heat pump water heaters move heat by extracting that heat from the air into a very cold refrigerant at a low pressure. So if we draw a line down the middle of the screen or the middle of our heat pump here, we have high pressure on the right-hand side of that line and low pressure on the left-hand side of it. So in our low pressure cool evaporator, we can blow air over that evaporator, which is a heat exchanger, extract that heat even when it's 30 degrees outside or 20 degrees outside, depending on the refrigerant that's in this circuit. And then we essentially moved a portion of that heat into that refrigerant. Now, if we pressurize that refrigerant with a compressor, we can bring that refrigerant up to a much higher pressure and a much higher temperature. So now that we're at a much higher temperature, we can go through another heat exchanger, a condenser. This is a refrigerant to water heat exchanger. And we're going to transfer a bunch of that heat that we got through the evaporator into domestic hot water. So we can take 20 to 30 degree air, source air, extract heat from it, and put that heat into water and make it above 120 degrees. Often heat pump water heaters can heat up to about 150 degree water. So there's a lot of available heat in that air that we can utilize in this heat pump circuit. So after we've dumped the heat into the water at our condenser, we go through an expansion valve because this is a circuit and this is modulating pressures on either side of this high pressure, low pressure circuit. And that brings us back to the original state, a cool, low pressure refrigerant that once again we can extract heat from. And so this process is much more efficient than gas or electric resistance heating, and why heat pump water heaters are going to be one of the star players in domestic water heating systems in the future. They are definitely going to move gas and electric resistance out of the market because they're much more efficient. And they result in those high efficiency system, or those high. They're great to help get to those high efficiency buildings and systems. And like I said, this heat pump cycle is a process, and so we typically have two ways to control this process. We have a single pass heating cycle and a multi-pass heating cycle. And they're pretty straightforward. Single pass means that we take the water at whatever temperature it's coming in at, typically around 50 degrees, and within one single pass through the heat pump, it's going to come out at 140 degrees or above our usable temperature. 120 is typically the temperature we're sending out to those building fixtures. So within one single pass, we've heated the water up all the way, or in this case, we've overheated it a little bit, and that's totally fine. So a single pass heat pump water heater is typically more efficient than a multi-pass heat pump water heater. Will also result in a more efficient use of your storage tank and is best suited for the primary heating load. Heating the water that comes in from the city at 50 to 60 degrees and heating that up to above 120 for use in our domestic application. Multi-pass heat pumps also exist, and this type of heat pump is not controlling the water flow rate through the heat pump. And so in this design, we're just trying to dump as much heat as we possibly can into that water circuit. And we're passing that water through the heat pump multiple times. So if we come in at 50 degrees from the city, we're often just adding 10 degrees of heat to the water in a multi-pass system cycle. And so that 50-degree water is heated up to 60 degrees on the first pass, second pass 60 to 70, 70 to 80, you get it until we get up to that 120 or above set point, whatever we have the heat pump set at. This is a less efficient process. As we're going through that heat pump more times, it ends up being over the course of a year or a day, it consumes a little bit more energy than our single pass equipment. But it has some advantages because we are just trying to dump 10 degrees of heat into that water. It's typically really well suited for our temperature maintenance loads because those systems were often sending out water at 120 to the building fixtures and it's coming back at 110. So what I'd like you to understand today is that there's two ways to operate those heat pump water heaters. Some manufacturers allow either or operation, and some manufacturers, specifically CO2 heat pump water heaters that use CO2 or R744 as the refrigerant, are only going to allow for this single pass operation. And so we have some strategies to deal with those aspects of system design, and we cover those in some of our engineering deep dive courses if you're interested in learning more. So I'm flying through this, but we only have an hour, so I have to go fast. Hopefully there might be some questions, and we'll take a break for questions at the end of this short primary storage discussion. So like I mentioned, heat pump water heaters are not instantaneous heaters. We need a place to store that hot water. The primary storage is that system or that component for the system. And so that primary storage tank can be multiple tanks. And this is very similar to a battery bank. When we have a large off-grid system, or if you look under the hood of a Tesla or all-electric vehicle, you're going to see multiple batteries. And we can connect those batteries either in series or in parallel. We can also do that for our hot water storage tanks. And typically it makes sense to connect them in series when we're working with single pass primary heat pump water heaters. And it might make sense to connect them in parallel when we're working with our multi-pass heat pump water heaters. And that really ties back to the discharge water temperature out of those heat pump water heaters. And in a single pass cycle, we can always guarantee that water to be above 120 or that usable delivery temperature. So pausing here for any questions. The Slido was not working today. And so if there's anything in the chat, Sean, let me know, or we can pause here for a moment and let you put any questions in the chat or question bar.
Colin, it doesn't look like we have anything right now for questions, but everyone feel free to ask anything now. It's a good time to put in your questions, and we'll get to it at the end most likely.
So we have our primary heat pump water heater. We have our primary storage tank or tanks. We can also have multiple primary heat pump water heaters, like I'm showing on the screen there. And then the next component is the temperature maintenance system. So what is the temperature maintenance system? Well, it's the system that's keeping the water in the distribution piping hot, because if Tim's at the end of the line here and he's the first one to get up for his job, this line over a period of no use might be a few 100 feet long. It might be a 3-inch pipe in a large multifamily building. It might reduce to a 1 or 1.5 inch pipe going up, serving multiple floors. Tim doesn't want to have to drain all that cool water that sat overnight out to take his early morning shower at 4 a.m., 5 a.m. And so we typically circulate the water with a hot water circulation pump to reduce the amount of wasted water we're flushing down the drain. And it's not just wasted cold water in that sense, it's wasted hot water because we've already heated this water, we've lost temperature of that water, and now we're going to drain it. And so it's part of that hot water load. And so it is a significant amount of energy. So with a circulation pump, we can just circulate that water through that distribution network. And that keeps it close to 110, 120 degrees, depending on where you are in this circuit. So the temperature maintenance system, it includes that distribution piping. It includes a mixing valve, typically in our large commercial buildings, and a circulation pump. Because as we're circulating the water through the distribution network, we need some way to mix these three streams of water: our hot circulation, which is around 110, our cool water, typically around 60 to 70 degrees, and our hot water from our heat pump system, typically around 130 to 150 degrees. The other component we have is a heat source. And so this is the heat source that's adding heat into the water to maintain the temperature in that distribution network of piping. So in the classic gas or electric resistance water heating system, we might not have a dedicated heat source as I'm showing here, where we've decoupled or separated the hot water circulation from the primary storage. So that circulation water is going to go into that tank and out of that tank. It's never going to interact with our primary system over here on the left-hand side of the screen. And we're going to cover why this is important and the value of the temperature maintenance system super quickly here. But we do speak a lot more in depth about this. So if you're curious, there's more training opportunities and more information out there on the web about the value of the temperature maintenance system. So heat pumps are very efficient, amazing devices at taking cold water and making it hot. So if we have our cold water connection to the city, we can feed that into a storage tank. There's going to be a sensor in that storage tank. Depending on where that cold water, hot water level rises or falls to, that's going to initiate a heat pump circuit or cycle, which is going to draw in cool water from the bottom of our tank. In a single pass arrangement, we're going to heat that water all the way up to the usable temperature, typically around 140 degrees Fahrenheit, and store that water in the top of our storage tank. And so this makes really good use of our storage tank, as we have a large volume of water that's at or above the usable temperature. And we have a small volume of cool water at the bottom of the tank that we can draw from to add heat to at a very efficient operating point. In our commercial buildings, we will often have a mixing valve. And so the hot water, because we might be storing it at 140 degrees, that might be a reason to have a mixing valve, or often is a reason. There's other reasons as well. And so that 140 degree water feeds into one side of the mixing valve, the hot side. On the other side, we have cool water coming in from the city, typically around 70 degrees Fahrenheit. And that water then mixes out and is delivered to the building fixtures closer to 120 degrees Fahrenheit. And so this is a really great, simple, really reliable heat pump water heating system. But like I mentioned earlier, we have that temperature maintenance aspect in our larger commercial multifamily buildings. So how do we deal with that, and why do we deal with it differently? If we simply put a hot water return loop on that piping, so we have some way to draw that water back, we put a circulation pump that runs at a slow but nearly continuous flow rate, we can discharge that water back into our tank. But if we discharge it back into the primary storage tank over a period without much hot water usage, we end up just mixing that tank with 110 to 105 degree return water from our hot water circulation system. What this does is it destratifies the tank. And stratification, what I mean is a lot of hot water at the top, a very thin transitional layer of tepid water, lukewarm water, and then a very defined profile of cold water. So high stratification, we have very defined layers of our water. With that return water mixing in continuously or nearly continuously into our primary storage tanks, we end up destratifying the tank. And so before, we essentially had a fully charged battery with this storage tank, as we had a lot of hot water all the way down to this temperature sensor here. Now we have a little bit of hot water at the top and a lot of mixed lukewarm water, maybe about 100, 110 degrees in the middle of the tank. And so that's not a very good efficient use of our hot water storage tank, as we're lowering the effective storage volume. And it also causes issues with the heat pump water heating cycle, because that single pass heat pump water heater might be pulling in 70-degree water, and then over time it's trying to put heat into already partially heated water. So if we assume this water is 110, it's trying to take heat out of the air and put that heat into 110-degree water, which is an operating point that's typically on the boundary of the heat pump cycle. So it might be able to do it, it might not do it very reliably, or it might not do it very efficiently. And so there's risk involved with this combined system where we're putting the circulation water back into our primary tanks. We do have solutions for this at Ecotope, and the Seattle Energy Code 2018 is also calling out this aspect of system design in the code. And so the solution is essentially to provide a dedicated heating source and temperature maintenance system so that we decouple the hot water circulation system from our primary. And two common approaches are the in-series swing tank, where we have an electric resistance heat source here, and we're plumbing this pipe in series, so it's going to the bottom of that tank, or in parallel with a dedicated multi-pass heat pump water heater, as these are really well suited for that recirculation load. Here, the system is connected in parallel, so the hot from the primary is connected to the hot outlet from that temperature maintenance, whereas over here we're connected to the bottom. I'm not going to any more details on these system designs and some of the key considerations for them, but we do cover these in in our deep dive seminar, as well as other heat pump water heater presentations. So there's a lot more information out there, but due to time, we're gonna leave it at that for now. And so our last component is the control system. And so, like I mentioned before, our residential integrated or unitary heat pump water heaters are packaged together. That package comes with a controller or some way to initiate that heat pump cycle and to stop it at the appropriate time. In our larger commercial systems, most of the manufacturers, if not all of them, have internal controls built in. And so this is the Colmac heat pump water heater from the Jackson Apartments building I showed earlier today. And that has a built-in internal control system that we can set our set points. We can set our set points up in there and tell that heat pump essentially when to come on, when to come off, make sure our defrost is programmed correctly for the environment it's in, and check a few other characteristics to make sure that that's operating at a very reliable and efficient operational point. But there are also external control systems that can integrate with the heat pump water heaters, as well as other components in our commercial heat pump water heating system. So if we have multiple backup devices that are going to help our heat pump water heaters on certain days of the year or in unfriendly climate conditions, the external control system is typically working very similarly to the internal controls of the heat pumps, but we need to ensure it's set up correctly for that heat pump water heater. And so it's really critical to engage with the manufacturer when setting up an external control system to ensure that the operating parameters and boundaries that you're establishing in that controller will be allowed and permissible for the heat pump water heater to operate at those boundaries. Other advantages to external controllers is alarm capabilities. Typically, we can connect these to a BMS or some other platform where we can not only trend the data and look at it remotely, but we can also provide alarms to building maintenance personnel or other people that are working on that system or responsible for maintaining it. And like with some of these earlier implementations of this technology, understanding what's happening and why it might have happened is really important whenever we have a problem. The internal controls of the heat pumps, depending on what manufacturer you're specifying, might have some of that capability, but to really ensure a really robust understanding of the system operation and how well it's performing, as well as any notifications on maintenance or alarms or other aspects, the external controllers really are really worthwhile in some situations. So although they're going to add money, cost to the project, there can be some great advantages, especially with regard to troubleshooting or fine-tuning the operation and maximizing the performance of these heat pump water heating systems. And so that brings us to our recap on the 4 components of a commercial heat pump water heating system. We have our heat pump. That's what's moving heat into water, and that is typically storing it in our primary storage tank, which is where we're storing our hot water. It's our battery bank. And then we have a temperature maintenance system, which is existing in all domestic water systems, or most for commercial buildings, especially the large ones. But in a heat pump water heating system, we might want to provide dedicated equipment to deal with that temperature maintenance load. And so we might have a dedicated temperature maintenance system in our commercial heat pump water heater systems. And then the last is controls. We need some way to turn on and off the heat pumps and other components in the system if they're aiding in backup or so forth. And I'll take a moment here to pause and to answer any questions. We have about 15 minutes left to cover really briefly system sizing and equipment selection, as well as a few points on Seattle City Lights code updates, or the Seattle Energy Code updates.
Yeah, Colin, it looks like we have a pretty well thought out question from Aaron. The question is, it looks like the smaller residential integrated units don't have an internal pump, but the larger commercial units do. Is the pump energy included in the performance data, COP, provided by manufacturers? And the follow-up is, does the full list of components providing power include fans, compressor, pumps, and controls? Are all these included?
Oh, that's such a great question. It depends on the manufacturer. Most manufacturers for commercial equipment will have a pump in the heat pump water heater. And so that pump will cycle cool water from your storage tank through the heat pump and discharge it back into that storage tank as hot water. I would say most manufacturers have that, and that is included in their reported performance values typically. There are some manufacturers, let's say you're doing a multi-pass system design, that give you guidelines on what size that pump should be, and maybe a manufacturer that they've a preferred manufacturer. In that case, it's not going to be included in that performance value. And that goes for fans too. I would say that I don't know of any heat pumps that don't have an air source fan or a fan on the evaporator. And so in most scenarios that I know of, that energy use for that fan is included in that heat pump water heating performance value, whether it's a capacity or coefficient of performance.
Aaron, thank you for that question. Really appreciate it.
Yeah, it was a great question. Very detailed. I love it. So the next thing we're going to talk about is key design considerations. We have some really critical key design considerations for the heat pumps, the storage, the temperature maintenance system, and the controls. And once again, I'm going to push you towards or guide you towards those other presentations we do on more of the engineering deep dive is what we call it, where we talk about the some necessary design considerations for, let's say, your storage volume and if you're connecting it in series or parallel. Today, our key design considerations are really with regard to the system sizing and equipment selection. Once again, this is an hour presentation, so we're looking at this at a high level. So hot water system design, we're looking at sizing first. We need to size for the hot water load. So what defines that hot water load? Well, it's the number of occupants in the building, of course, how much hot water those occupants use per day. We're going to see a different hot water usage per day if it's a residential building compared to an office. You might only use a few gallons of hot water in an office situation, and you might use closer to 20 gallons in a residential application. And then the last one is the building type, and that really ties back to this load profile that I'm showing here on the screen. So right here, top right, we have the load profile from a multifamily building. And so this shows the design day in blue, the peak day, peak water usage, and a more average day in orange here. So we can see that there's a big morning rush. People use a lot of hot water in the morning when they're taking showers and getting ready for their day. There's a little bit of a calm in the afternoon or early afternoon. And then once we all get home and we start cooking and cleaning up, we use hot water again and maybe doing laundry and showering. So that hot water load profile is really key when sizing heat pump water heaters. We need to size the system so that there's enough hot water for this big draw period in the morning. And then we also need the heat pump water heater to be able to recover the storage tank volume before there's another peak draw in the afternoon. Typically in gas and electric resistance systems, we're trying to recover within this period. So it's typically a 2 to 3 hour recovery. So very quick. We used hot water, now we want to store that or heat that water again and store it in a tank. We can do that with the heat pump water heating system, but it just adds unnecessary cost to the project. And so I really encourage you to evaluate when you need to have recovered that system by. And so that might be a 6 hour period instead of a 3 hour period that you're more used to working with. But essentially, we need to be able to maintain hot water during these two big load profiles. And typically we do that by storing water in a storage tank before this load happens so that we're fully charged before people start using water in the morning. But it's really important to understand when those loads are. So if you look on the left-hand side, we have our hot water loads for food service are going to be more in the afternoon. Big one right after lunch, cleaning up, and a big one right after dinner, cleaning up once again. Motels, more usage in the morning because they typically kick us out by 11 or 12, and we're on our way. The EcoSizer is a free web-based online tool that is designed to help you understand and size your heat pump water heating system. So right now, this tool is only applicable to hotel, motel, and multifamily buildings as it is using that load profile. However, we are adding more load shapes and profiles so that this can be applicable to office buildings, fire stations, and a wide range of building types and applications. I don't have enough time to show you how to use this tool today, but there is a very straightforward numbered list with 8 points or 8 steps to get you through this tool. And in the end, you're going to get a graph like this where it outputs your recommended system size and what this system was sized for and some other information on a temperature maintenance system. And this blue bar is, you can toggle it around. So if you want to evaluate and trade off between the required heat capacity you might need and the required storage volume, you can do that. So typically gas systems were sized with very low storage volumes and very high heat capacity. In heat pump systems, heat capacity is typically more expensive than storage volume. So it might be advantageous for you to reduce the amount of heat capacity you need and increase the storage size. You're still going to meet the load. You're just trading off between those two parameters. And that's really one of the greatest values of this tool known as the EcoSizer. And you can find it at ecosizer.ecodope.com. So the last point is equipment selection in the last 8 minutes here. So we have multiple heat pump water heater products out there. This is a list that I pulled together a while ago. There's definitely been some updates, and these manufacturers like Rheem and A.O. Smith typically also do have split system commercial heat pump water heaters, not just these smaller residential units. Although this A.O. Smith is a light commercial integrated or unitary device. So it's applicable to those small commercial applications or maybe a restaurant. So lots of options out there, not as many choices as the cereal aisle in the grocery store, but all of these have different values and might be more applicable in one situation than another. What I want to highlight to you in the last few minutes is one of those key criteria or one of those key aspects of that heat pump water heater is the refrigerant that's being used in that heat pump cycle. So our refrigerant CO2 or R744, Sandin or Sanco 2 and Mitsubishi, as well as Maikawa and other manufacturers have CO2 heat pump water heaters. These work in a wide ambient air temperature range. So this is the air temperature up here. So we can operate those down to -10. So if you're in a cold climate, you're probably looking at a CO2 heat pump water heater. If you're on the West Coast in a mild climate, maybe in California or parts of Seattle, R134A heat pump water heaters are, there's numerous available that are commercially sized, and those are going to work at warmer temperatures. They're not going to operate below 40 degrees, putting heat into the system. You can get clever in Seattle and put these in an underground parking garage, which acts as a buffer space to keep that air temperature always above that 40-degree threshold. And this ends up working out really well for these R134A devices. Most of the heat pumps that have been available for the last 10 years have been R134A. It's great to see CO2 coming on the market because this opens up a lot more opportunities for those heat pump water heating systems. And then 410A, this is the refrigerant that's used in the VRF systems for those large space conditioning heat pump systems. But there are also manufacturers that use this for heat pump water heaters. Once again, these can work down to cooler air temperatures. However, they're a much higher global warming potential. So if any of this refrigerant leaks, it's very toxic compared to that CO2. It will add a lot of global warming potential to the environment. And so CO2 is much more environmentally friendly, much more forward thinking. But there are R410A heat pumps that are out there and can operate at cooler air temperatures than, let's say, the R134A, which is slightly more environmentally friendly, but still well above our baseline of CO2 as a GWP of 1. And so the other thing we need to understand is sizing our heat pump for the air temperature or the design day we're going to see. And so the heat pump water heater manufacturer will produce a submittal sheet or a specification sheet, and it might say 120,000 BTUs per hour on that specification sheet. That rating point is typically at around 60 or 70 degree air temperature. When we actually look at the design conditions that heat pump will operate at, if it's going to be in Seattle, we're going to be closer to 20 degrees on our design day. We're only going to get 110 kBTU out of that heat pump water heater. So it's really critical for you to understand and when you're sizing and specifying your system, to understand what the design air temperature is and how the equipment performance is impacted by that air temperature. This is for a CO2 heat pump water heater. So you can see is we're generating heat down here low on the ambient air scale. But if this was for R134A heat pump water heater, we wouldn't be heating on the left-hand side here of 40 degrees Fahrenheit. So that wouldn't be heating water. The other thing to look at is the inlet water temperature. You can see that if our inlet water temperature is already hot, it's hard to put heat into that water. And so we're not going to have as much capacity at that elevated inlet water temperature as we do at that lower inlet water temperature of 45. So definitely some things to consider there. And if you're interested in this, join one of our other presentations. And then the last thing to discuss in our 3 minutes is how these systems are delivered to the market. In the past, we've had custom engineered systems. This is the woodworker approach, where you buy your lumber from your local sawmill, plane it down, put an edge on it, joint it, cut it to shape, and build yourself a chair. You can do this. It takes a special skill and background knowledge of the trade to make this happen, but this is definitely an option to result in a very reliable and efficient system if you understand how all the pieces are interacting and with each other. There's the Ikea approach, which is more of the specified built-up system. Here, all the pieces are coming from one manufacturer or one distributor. And so they're guaranteeing that this piece will fit with this piece and these will communicate together. And it's a much more guided approach to getting the system in the market or in your building. So they give you that set of instructions of how to connect these pieces together and what the set point should be in this specified built-up system delivery approach. And then the latest and greatest, which is still new, but Mitsubishi was at AHR this past year with one of these packaged skids, is a fully packaged system where everything is assembled and delivered in often a single package or two packages that kind of meet up together to serve the water heating load in the building. And so here you're going to have the storage tanks, the temperature maintenance system, a heat pump, and a control system all packaged together. Your plumber, your electrician will connect the water and electricity to these. And after that and commissioning, you should be off and running. So there's a lot of design burden that's been taken out of the engineer's world here and brought into the manufacturing facility for a more reliable and repeatable heat pump water heating system. And then the last is Seattle Energy Code updates. And like I mentioned early on, for group R1 and R2 occupancies with central service water heating systems, air source heat pumps are required, not fossil fuel or electric resistance. R1 and R2 are multifamily greater than 3 stories or any hotel or motel. So if you're in the Seattle area, under the Seattle Energy Code, you're now required to have a commercial heat pump water heating system. And I mentioned also earlier that there's some requirements on system design and configuration. There's also other requirements on sizing, alarms, temperature maintenance. That's that system design and configuration. And there's a great resource. I love these tips as an engineer. So if you look up SDCI tip 424, that's going to bring you to the tip, which is a bunch of very clearly laid out information on 2 pages, specifically regarding heat pump water heating systems for commercial applications and the code requirements around them. So you don't have to navigate through that large code book binder PDF that you have. The SDCI tip is typically 1 to 2 pages of the really pertinent information on these systems and the requirements. And there's other resources available, EcoSizer, the Advanced Water Heating Specification by NEA and Seattle Energy Code, as well as other trainings and opportunities to learn more about heat pump water heaters and those systems. So many thanks to our partners at Seattle City Light and the Lighting Design Lab, and I will hand it back to Katie here.
All right, thank you everybody for coming. We will post some more upcoming trainings in the next couple of weeks, but we have a couple of week break. This webinar was recorded and will be put up on our website within the next week. Thank you, everyone. Have a good day.
Thanks.
Thank you, everyone. Great job, Colin.